Imagine for a second that you are holding an apple, like just a regular apple.
Right.
You drop it right here on Earth, and obviously it falls down to the floor.
Right.
Now imagine you hop into a spaceship, fly 2 million light years away to the Andromeda Galaxy, and drop that exact same apple. You'd probably expect it to fall exactly the same way, right?
Yeah, I mean, following the exact same mathematical script written by Albert Einstein.
Exactly. But what if it didn't?
Yeah.
What if, in that specific corner of the cosmos, the apple fell sideways?
Or, what if it just shattered into a million pieces because the fundamental laws of chemistry simply don't work the same way out there?
It sounds totally like science fiction.
It really does.
That's-
But this is actually the exact debate currently rattling the foundations of modern astrophysics. I mean, we've spent a century building a very clean, very centralized view of reality. We desperately want to believe that the cosmos is just this single, unified kingdom governed by one set of absolute rules.
Right. But the deeper we look, the more that beautiful universal script starts looking, well, a lot less like a cosmic constitution.
Yeah.
And a lot more like a set of local neighborhood regulations.
Yeah.
So today, we are doing a deep dive into a massive paradigm shift in how we understand reality itself. We're looking at a fascinating July 2026 paper by Daniel Correa titled The Fragmented Cosmos.
And we're going to completely bypass the dense equations and shortcut you right to the frontier of this debate.
It truly is a frontier. I mean, for over a century, Einstein's theory of general relativity gave us this incredibly elegant universe.
It did. The assumption has always been that the physics operating in our terrestrial laboratories right now are identical to the physics operating in the deepest, most distant vacuum of space.
But we're starting to realize that our maps of the universe might be heavily biased by our own cosmic zip code.
Exactly.
Okay, let's unpack this, because framing it correctly is crucial right out of the gate. This isn't about just tearing down Einstein for the fun of it.
No, not at all.
Science isn't built by setting fire to old textbooks. Like, Newton wasn't entirely wrong about gravity, His math just turned out to be a local truth for our immediate low-speed environment.
Right. Einstein expanded that map.
And now, we might be looking at the next great expansion. The discovery that the universe isn't some homogeneous, uniform fabric, but a wild, dynamic, cosmic mosaic.
To really grasp this mosaic, we have to start by pulling up the floorboards of reality.
Okay, I'm ready.
I want to ask you a question that sounds absurdly simple, but it's actually the core of this entire debate. If you were to completely remove all matter and energy from the universe,
Like everything.
everything, take away every galaxy, every star, every atom, every single photon of light, what is left?
My instinct, and I think the instinct of anyone listening right now, is to say nothing.
Nothing.
But a very specific kind of nothing, like an empty room, just a three-dimensional void floating there, patiently waiting for someone to put furniture back in it.
Yeah, with a clock ticking away on the wall, measuring time, even if absolutely nothing is happening.
Right.
And that instinct is the direct result of how traditional science has taught us to perceive reality. We've been trained to imagine space and time as a literal physical fabric.
Like a stage where the movie of the universe plays out.
Exactly. Einstein unified those into space-time, showing that this stage isn't rigid. The mathematics treat it as a real, dynamic, physical entity that can, bend, stretch, and ripple.
But wait, this is where the fragmented cosmos throws a massive wrench into things. What if space and time aren't real physical entities at all?
This is the uncomfortable alternative that gets swept under the rug.
Yeah, the paper suggests that maybe they are just abstract metrics, meaning there are mental tools that human beings invented to order and measure distances between objects and the sequence of events.
If we connect this to the bigger picture, the distinction is monumental. Because if space-time is just a metric, it's not a physical fabric that can stretch or bend. It's a pure concept.
It makes me think of the grid lines on a globe.
Oh, that's a good analogy.
Like, we use latitude and longitude to navigate. They're incredibly useful tools for measurement. But if you walk outside your front door right now, you don't physically trip over the equator.
Right.
You don't get tangled up in a longitude line.
Yeah.
So are physicists basically confusing the map for the actual territory?
I'd actually push it further. I mean, they haven't just confused the map for the territory. They've insisted the map is the territory.
Oh, wow.
And if you accept space-time as an immaterial abstraction, like just a human measurement tool, the entire scaffolding of contemporary physics begins to creak.
Because if this invisible stage isn't a universal physical object, then the true universe doesn't have a medium to enforce a single absolute law.
Precisely. Physical interactions would have to emerge locally, depending on the environment.
Okay, but I can already hear the defense from the physics I learned in high school, though.
Let's hear it.
If space-time isn't a physical thing that stretches and bends, how do we explain the technologies we use every day that supposedly prove Einstein right? I'm talking about the GPS and the phone sitting in your pocket right now.
Ah, the classic GPS counterstrike. It is the ultimate go-to example when defending the physical reality of space-time.
Well, it's a good example. The story goes that the atomic clocks on GPS satellites orbiting the Earth experience time faster than clocks down here on the surface.
Right, because they are further away from Earth's gravity and they are moving at high orbital speeds.
Yeah, and if engineers didn't use Einstein's equations to literally correct that time difference, our navigation apps would drift by kilometers every single day.
That's the standard narrative, yeah.
So standard physics looks at that and concludes, boom, physical time itself is dilated, the fabric of time stretched. How do you explain that without a stretchy space-time fabric?
Well, you explain it by actually looking at the physical mechanics of the clock rather than inventing an invisible, stretchy dimension.
Okay.
Long before this was a mainstream debate, a physicist named Hendrik Lorentz proposed a perfectly valid alternative. He asked, what if time itself doesn't change?
Wait, really, time just stays the same?
Yeah. What if instead the local gravitational and energetic fields physically alter the behavior of the clock's internal mechanisms?
Oh. Here's where it gets really interesting, because an atomic clock isn't just a digital stopwatch counting abstract numbers, it's a physical machine.
Exactly. An atomic clock works by measuring the vibrations of cesium atoms. Think of the atom like a tiny, incredibly precise pendulum.
Okay, I'm picturing it.
Down here on Earth, that pendulum is swinging in a very strong gravitational field. Up in orbit, the gravitational pull is much weaker, but the satellite is moving at incredible speeds through different energetic fields.
Right.
Lorentz argued that these local physical conditions literally, mechanically affect how the cesium atom vibrates. The pendulum gets bogged down or speeds up based on the local environment it is traveling through.
Oh, wow. Okay, think about a wooden ruler.
A wooden ruler.
Yeah, if I take a pristine wooden ruler into a super humid jungle, the wood absorbs moisture. It swells and warps. The ruler physically gets slightly longer.
Right, the humidity physically changes it.
Exactly. But when I measure a table and the numbers are off, I don't look at the warped ruler and declare, my God, space itself has expanded in this jungle.
Right. You don't assume space changed.
No, I just know the local humidity warped my measuring tool.
That is the perfect way to look at it. The local environment altered the physical object, not the fundamental dimension of reality.
So in the GPS example,
The satellite's drift doesn't happen because the fabric of time warped. It happens because the specific energetic conditions of being in orbit alter the physical oscillation of the cesium atoms. It's a mechanical change, not a temporal one.
but if the warped ruler explanation works so well and doesn't require us to invent magical stretching fabrics, why does institutional science cling so tightly to the space-time idea?
Pragmatism,
It's
most.
just pragmatism.
Yeah, I mean, for current physics, it is methodologically much simpler to assume that the geometry of the shared board, the space-time grid, changes uniformly.
Because the alternative is a nightmare to calculate.
Exactly. The alternative is trying to calculate how invisible local forces alter every single particle in the universe in slightly different ways depending on exactly where they are. Calculating space-time geometry is basically a pragmatic, mathematical shortcut.
But it relies on a massive, highly arrogant premise.
Hmm.
Like, we are assuming that the physical laws governing atoms in our cozy little earthly laboratories apply perfectly to the chaotic, deep vacuum of space.
Yeah, we are projecting our local terrestrial bias onto the entire cosmos just because it makes the math easier on our computers.
And that Earth-centric bias forces a very crucial question. What actually happens when we try to do science millions of light years away from our home turf?
Well, when we were playing at home, we look like geniuses.
Right, we can predict a solar eclipse in our own solar system 10 years down the line, down to the millisecond.
But that's because we are using equations that were calibrated and tested right here in our own neighborhood.
So what happens when we look further out?
Well, modern astronomy isn't content staying in the neighborhood. We have these incredible instruments now, space telescopes like James Webb and Chandra,
They're amazing.
truly.
Yeah.
And we are peering at distant exoplanets and places like the M51 galaxy, which is roughly 28 million light years away.
That is absurdly far.
It is. And when astronomers try to mathematically predict their orbits, like to predict an eclipse or a planetary transit in another galaxy, the classical models start breaking down.
Yeah, the paper dives into this phenomenon called transit timing variations, or TTVs.
Right.
For anyone listening who's unfamiliar, a transit is when a planet passes in front of its star and we see the starlight dim just a tiny bit. It's supposed to happen like clockwork.
Exactly, like clockwork based on our math.
But with these distant galaxies, the planets simply do not appear when our classical Earth-calibrated math says they should. They are late or they are early. The script is fundamentally wrong.
And this is where we run headfirst into what philosophers of science call the uniformitarian principle.
Which is what exactly?
This is the absolute foundational assumption of modern astrophysics. It's the belief that the laws of nature, gravity, mechanics, light are identical and homogeneous throughout all space and all time.
But calling it a principle almost makes it sound like a proven law, when really, according to this deep dive, it's a methodological act of faith.
It is entirely an act of faith. We accept it as true out of sheer necessity.
Because if we didn't,
Because if we admitted the truth that gravity might work based on entirely different mathematics in the M51 galaxy, our ability to do science at a distance would completely collapse.
wow.
We wouldn't be able to confidently interpret the light reaching our telescopes because we couldn't trust the physical rules that originally emitted that light millions of years ago.
So if you're listening right now and wondering how scientists deal with this, they basically put on blinders.
Yeah, they have to.
To avoid an existential crisis, they look at these transit timing variations, these late planets, and they just blindly assume that there must be other invisible planets out there causing a gravitational pull and messing up the schedule.
It's a quick fix.
They are effectively inventing ghost planets just to protect their mathematical models because they are calculating in the blindness of vast distance.
What's fascinating here is how science reacts to anomalies. Rather than questioning the foundational assumption that our local laws apply everywhere, we invent invisible entities to make the equations balance.
We refuse to accept that the rules of the game might change depending on the stadium.
Exactly.
But I have to push back here on behalf of the skeptical listener.
Sure.
An orbit variation is one thing. You can hand-wave that away with a ghost planet. But is there hard, undeniable physical proof that the fundamental underlying laws of nature actually change depending on where you are in the universe?
There is. And for that, we have to look at the crack in the constants. Specifically, the mystery of the fine structure constant known as alpha.
Okay, for those of us who don't have a quantum mechanics textbook on our nightstand, what is alpha and why does it matter?
In quantum physics, there are certain numbers that are just pure numbers. They don't have units like meters or seconds attached to them. They are the underlying code of reality.
Like the source code.
Yeah. Alpha sits at approximately 1 over 137. It dictates the exact strength of the electromagnetic interaction.
So it controls magnets and electricity.
And much more. In practical terms, it determines how rigid atoms are, exactly how electrons orbit a nucleus, and how light interacts with matter.
So it's basically holding everything together.
Literally. If the value of alpha changed even slightly by just a tiny fraction, stars wouldn't be able to fuse elements properly. Carbon wouldn't form. The fundamental chemistry necessary for life simply wouldn't exist. Our reality depends on alpha being exactly 1 over 137.
So it's the universal load-bearing wall. If it shifts, the whole house comes down.
Precisely. Everyone assumed it was absolutely immutable. But then an international team of astrophysicists, led by John Webb, decided to test it.
How do you even test that?
They analyzed the light emitted by quasars. Quasars are monstrously bright, primitive galaxies that are incredibly far away. Their light has been traveling to us across deep space for billions of years.
But how does looking at old light tell you if a quantum number changed?
Because light acts like a barcode. When elements in space absorb light, they leave black lines on the color spectrum. It's a very specific barcode for every single element.
Okay.
Webb's team looked at the barcodes in this ancient quasar light and compared them to the barcodes of elements tested here on Earth.
And then they didn't match.
They didn't match.
No way.
But it gets weirder. They detected what is called a spatial dipole. Think of it like a cosmic seesaw.
A seesaw.
Yeah. When they looked in one direction of the deep universe, the barcodes shifted in a way that proved the value of alpha was slightly smaller.
Okay.
But when they looked in the exact opposite cosmic direction, the barcodes shifted the other way. Alpha was slightly larger.
This raises an important question. Actually, no, it drops a bomb on conventional physics.
It really does.
If fundamental constants of nature vary depending on your spatial coordinates, like if the rules of electromagnetism literally change depending on which direction you look, the universe completely ceases to be a uniform plane.
It shatters the uniformitarian principle entirely.
So what does this all mean? Let's bring this right down to your everyday life as a listener.
Let's do it.
It means that the water in the glass sitting on your desk, or the very chemical bonds holding your DNA together right now, might physically not be able to exist in another corner of the universe.
Right.
Because the local laws of chemistry and physics over there wouldn't allow those atoms to hold together.
It means that physics and chemistry are inherently local phenomena. The cosmos truly is a mosaic of different realities. The rules of our solar neighborhood simply do not govern homogeneously across the entire universe.
That is just mind-bending. But if chemistry and gravity are fluid and localized like this, how does that impact the really big stuff?
What do you mean?
The biggest unsolved mysteries of the universe. Because I'm thinking about invisible things scientists invented to make their math work, I immediately think of dark matter.
You'd be right to go there. This fragmented cosmos model completely reshapes how we view dark matter. Modern astrophysics relies heavily on dark matter and dark energy to explain things it can't otherwise justify.
Right, because when astronomers look at a spinning galaxy, there isn't enough visible stuff, stars, gas, planets, to generate the gravity needed to hold it all together at those incredibly fast rotation speeds.
Exactly.
According to Einstein's math, the outer edges of the galaxy should just fly apart into deep space. But they don't.
So instead of concluding that Einstein's math might not perfectly apply to a galaxy a billion light years away, cosmologists added dark matter to the mathematical equations.
Even though we can't see it.
It's a completely invisible ingredient. It doesn't interact with light. We have never directly detected it in a laboratory. Yet to make the standard models work, dark matter and dark energy supposedly make up 95% of the entire universe.
So if you're listening to this right now and feeling confused by dark matter, you're not crazy. The astrophysicists are literally making up 95% of the universe just to make their equations balance.
It sounds absurd when you put it like that.
It's like hiring a plumber to fix a leak, and instead of admitting he brought the wrong-shaped pipe, he just wraps it in 95 layers of invisible duct tape and says, "There, the math works now."
I love that analogy.
It feels like a massive institutional coping mechanism.
It is a definitive symptom of a scientific model in profound crisis. The absolute refusal to let go of this Copernican idea that our earthly laws must govern the entire cosmos shows a preference for technological convenience over philosophical truth.
But there are alternatives, right?
Yes. Theories like modified gravity or MOND.
How does MOND fix the duct tape problem?
Well, MOND suggests that we don't need dark matter at all if we just admit that at incredibly large cosmic scales, the laws of gravity themselves change.
Well, so it adapts.
Right, gravity isn't a fixed constant. Its mathematical behavior adapts based on the region and the scale of the acceleration.
But institutional science fights theories like that tooth and nail because it threatens that universal space-time scaffolding we talked about earlier.
It threatens the core of their model.
Defending space-time isn't about objective truth anymore. It's about institutional momentum. But pointing this out, being skeptical of dark matter or the universality of Einstein isn't being anti-science.
Not at all.
Skepticism is the engine we need to shatter that arrogance. We have to stop forcing the universe to fit our Earth-sized equations.
And that requires a massive shift in how we do physics. We have to move away from absolute realism, the idea that the grid exists before the matter, and move toward what philosophers call relationism or emergence.
Let's break that down, because emergence sounds pretty heavy. How does that work in plain English?
Okay, think about a massive crowd of people at a stadium doing the wave.
Oh, yeah, sure.
There isn't an invisible grid dictating how the wave moves.
Yeah.
The wave emerges purely from the local dynamic relationships between the people sitting next to each other.
Right, they just react to the person next to them.
Exactly. Relationism says the universe works the same way. The rules of space, time, and gravity aren't a pre-existing sage. They emerge locally based on how matter and energy interact in that specific neighborhood.
So as we wrap up this deep dive, let's summarize this journey.
It's been quite a ride.
We started with the comfortable engineering-like precision of universal fabric, a single stage where the rules never change, from Earth to Andromeda.
And we've completely shattered that.
Right, moving to a cosmos that is a vast, decentralized patchwork of local laws. The speed of a ticking atomic clock, The orbit of a distant planet, or even the chemical bonds of a water molecule might be entirely dependent on local neighborhood regulations.
It changes absolutely everything about how we perceive our place in reality.
It really does.
The next time you walk outside and look up at the night sky, you shouldn't just see a single, uniform kingdom governed by one unbreakable law. You are looking at an infinite patchwork of vastly different territories, each operating with its own unique rules of reality, its own specific physics and chemistry.
It's terrifying, but also infinitely more beautiful than a rigid grid. And it leaves me with one final, deeply provocative thought that I want you to mull over long after this deep dive ends.
What's that?
Well, if our local physical laws, like the exact gravity, the exact fine structure constant that allows atoms to hold together, are essentially just specific neighborhood regulations, could human consciousness and biology be entirely confined to our specific region of space?
Oh, wow. We always assume life adapts to the universe, but what if life can only exist in the specific, highly regulated local zone?
Exactly. What unimaginable, bizarre forms of matter or entirely different, incomprehensible forms of life could exist right now in a cosmic neighborhood where the fine structure constant is vastly different?
Completely outside our understanding.
Out there living out a reality we literally don't even have the physics to perceive because our maps simply don't cover their territory. Just something to think about the next time you drop an apple.